So let's find and classify all the critical points for this one. Yesterday we only looked at polynomials, so I just want to extend that and look at a few that are not polynomials. So we start the same way, derivative. So the derivative of 4 is 0, that goes away. 1/3 comes down, x to the negative 2/3. Keep in mind what that means. It's like 1/3 times the cube root of x squared. Does that ever equal 0? No. But I still have a critical point. What is it? 0. Why? It's undefined at 0. So the one critical point we have is the x equals 0. Critical points are where it's 0 or undefined. So then, if we test this, something smaller and something bigger, plug those into the derivative. So if I put in a negative 1 squared is 1, cube root is 1, so I get 1/3, that's positive. If I put in a positive 1, I get 1 squared is 1, cube root is 1, so 1/3 is positive. These critical points are where we might have a maximum or minimum. It doesn't mean we have to. So in this case, if it's the same sign on both sides, there is no extremum, or no max or min. Extremum is just another word for the maximum and minimum. Any questions there? So now I want to talk about the second derivative. So if I look at these functions, okay, f and g, we could draw in the tangent lines. They look at these. We know that all these tangent lines would have a positive slope because the original graph was increasing. These would have a negative slope. The second derivative is the derivative of the first one. So it's like the derivative of those lines there, essentially. What it's going to tell us is how the slope is changing from the first derivative. Okay, so let's kind of wrap our minds around that. If the function is increasing, the first derivative is positive. The second derivative tells us what's happening to the slope of these lines. So if I'm looking here, these, as we go, they are getting steeper. So the slopes are increasing, so the second derivative would be positive on that one. This one, if I look at these tangent lines, as I go on, those slopes are getting smaller. So their slopes are decreasing, so the second derivative would actually be negative. Now if you look at the original graphs, what's the difference in the original curves? So just looking at the original, here I said the second derivative is positive, and this one the second derivative is negative. They're both increasing from A to B. The difference is the curvature of the graph. This one is curved upwards, it's called concave up. This one is curving downward, that's called concave down. So the second derivative tells us the concavity. Concave up, think about like it could hold water, okay? Concave down, it couldn't, it's curving downward. So just looking at this graph, like this section, is that concave up or concave down? concave down, it's curving downward. Okay, after that, this section right here is, really it doesn't switch until more like here. This section is curving upwards, so that's concave up, it could hold water. Okay, from here to here, now my graph's kind of switched and it's curving downward, so that's concave down. This is concave up. What's this section? Still concave up. What about this section? Concave down. Do you guys understand the difference between concave up and concave down? So, I remember the order I put all this stuff in here. Okay. So the concavity test, that's the little box we're going to fill in. If the second derivative is positive, that's concave up. When the second derivative is negative, that's your concave down. Okay. So far, so good? Let's look at this example. So this figure shows a population of honeybees. I want to know how the population rate increases over time. So we look at this. The x-axis here is our time, the y-axis is the number. So we can see the population is going up, the number of bees is going up. But how does the rate of that increase change? Like at the beginning, they're going up. Are they going up quickly? No. So it's a slow increase at the beginning. What happens in the middle? Really sharp increase, and then kind of flattening out again. Still going up, so the rate is increasing, the population's increasing the whole time. But we can see it increases really quickly in the middle, and on the ends, not so much. Second question, when would this rate be the highest? So when would I have the highest rate of growth in my population? Look here, about 12. Is that about the steepest point on our graph? I agree. So highest at 12. Okay. So when is this graph concave up and concave down? I use CU for concave up and CD for concave down. Can you tell me the intervals? What's this start out as? Concave up or concave down? Concave up, starting at 0 until when? And then after 12, what's it doing? Concave down. So that point where we had the sharpest increase, that's where the curvature of our graph changed. That point, so we know when we switch from a maximum to a minimum, that's a critical point. When we change from concave up to concave down, that is what is called an inflection point. So an inflection point is a change in the concavity. This leads us to our second derivative test. So first derivative test we use to tell maximums and minimums. Second derivative tells us if the first derivative is 0 and the second derivative is greater than 0, it's a local min. Okay, let's think about what that means. If the first derivative is 0, we have either a maximum or a minimum, right? So if f prime is 0, you've got one of these. If the second derivative is positive, that means it's curving upward. So it would have to be this one right here, which means you have a minimum. If the first derivative is 0, so either a max or min, and the second is negative, that means it was curving downward, that is a local maximum. The second derivative test, it's used for finding maximums and minimums. Personally, I don't use it a whole lot because the first derivative test tells us maximums and minimums, and it's not all that difficult to do, is it? The only thing this would save you is on a problem where I asked for everything, the maximums, minimums, the concavity, all of that. You could get away with just making one sign line instead of two. But I found that in general, this is just one more thing for people to remember, and they prefer just to do the first derivative test. So we can do the maximums and minimums just how we were doing them yesterday. We don't really have to use this. Alright, let's try to draw a graph that meets all of these requirements. And there is a typo on this. The second condition should say f double prime is greater than 0. Sorry about that. Okay, so let's read our conditions. F prime of x is greater than 0. So the first derivative is positive from negative infinity to 1. And f prime of x is less than 0 from 1 to infinity. So my first derivative was positive. That means my function was increasing or decreasing? Increasing. And then at 1, we switched, and now it's decreasing. So what happens at 1? We have a local max at 1. Okay, second thing. The second derivative is positive, so that means concave up or down. Up from negative infinity to negative 2 and 2 to infinity. It is negative from negative 2 to 2. So, that means we have inflection points at 2 and negative 2. That's where the concavity changes. Let's go ahead and read this third condition, and then we'll start drawing some things. The limit as you go to negative infinity of f of x is equal to negative 2. So as this graph is going forever in the negative direction, we have a horizontal asymptote at negative 2. The limit as x approaches infinity of f of x equals 0. So as you go forever in the positive direction, your horizontal asymptote is at 0. Alright, more than one possible graph. I know I have to have a maximum at 1. I don't really know where, so I'm just going to put one somewhere. Okay, until I get to negative 2, my graph is concave up. So that means it would hold water, right? This is a horizontal asymptote, so it's approaching that. So I have a concave up graph. After 2, it's going to switch to concave down. Okay, I know this is a maximum. So something like this. And I'm going to stay concave down until I get to positive 2. And then at positive 2, we have a very slight change to concave up again. And it's approaching that asymptote. inflection points, they're not an, it's not like a maximum or minimum where it's a real drastic change, just a slight change in the curvature of your graph. Typically, when we start graphing these functions, I'm just going to have you put like an X on your inflection points just to kind of show that you're aware that's where you're very slightly changing the curvature. Let's find the concavity based off some equations. Okay, I think that will be a little bit easier. I know these drawing graphs from conditions is kind of difficult. This is something we're working towards. But we'll just do them here and there to practice. Alright. Test this function for concavity. That means tell me where it is concave up and concave down. I did not ask for maximums and minimums, so we don't have to give them. If I did, what would you do to get maximums and minimums? We do the first derivative, set it equals 0, and make our sign line. Okay, so for concavity, I need the second derivative. So first derivative would be 3x squared minus 6x. Second derivative would be 6x minus 6. Inflection points are really like your critical points of the second derivative. So anywhere it's 0 or undefined. Is this ever undefined? No, so just set it equal to 0. So x equals 1. That is the inflection point. From here on out, I'm probably just going to put IP for inflection point. So that's where the concavity might change. Doesn't mean it has to, but it could change there. To test it, we'll just do the sign line. So you need something bigger and something smaller. I need to know if my second derivative is positive or negative, because that's what tells us the concavity. So I am putting these points into this second derivative. So if I put in a 0, I get 0 minus 6, which is negative. Put in a 2, 12 minus 6 is positive. So what that tells me is this graph is concave down from negative infinity to 1, and it's concave up from 1 to infinity. I'd like to do one example where we find everything that we've figured out how to do the past 2 days and use it to draw a graph. So, here's my function. Yesterday we talked about increasing, decreasing, max, and min. So that's where I'm going to start. What do I have to do to get that stuff? First derivative. So that would be a 4x cubed minus 12x squared. Okay. To find the increasing, decreasing, max, and min, I need to find the critical points. So I could pull out a 4x squared. You set that equal to 0, what are your critical points? 0 and 3. So then we did the sign line. Test points smaller, in between, and bigger. And where do I plug those things in? the first derivative, because I need to know where it's positive or negative. So if we put in a negative 1, negative 1 squared is positive, so 4 times 1 is positive. Negative 1 minus 3 is negative, so that section's negative. If I put in a 1, 4 times 1 squared is positive. 1 minus 3 is negative, so that section is also negative. If I put in a 4, 4 times 4 squared is positive, 4 minus 3 is positive. So that's positive. Okay. So where is this graph increasing? It's decreasing on both of these. Can you plug 0 into the original function and get an answer out? It's not a fraction, so can't I plug a 0 in? So as long as it doesn't make the original undefined, you can combine those and just say from negative infinity to 3. Now if there were like a vertical asymptote at 0, then I'd have to break them out and list the two intervals separately. Okay, local max and local min. So if I look, this one didn't change. At 3, we went from decreasing to increasing, so that is a local min. So f of 3 equals, where do I plug that 3 in? The original. So 3 to the 4th is 81 minus 4 times 3 cubed. What do we get? Okay, that's the first step. That's like what we did yesterday. Today's piece, the concavity, we're just adding to this. So we have to do the second derivative. I recommend, it's going to be a lot easier to do the derivative where we were at before we factored this, so you don't have to do a product rule. So that would give me a 12x squared minus 24x. So that's my second derivative. Take out a 12x, set that equal to 0. So my inflection points are what? So then we can do a sign line for those. So smaller than 0, maybe a negative 1. In between 0 and 2, be a 1, bigger than 2. And where do I plug those in? The second derivative. So if I put in a negative 1, 12 times negative 1 is negative. Negative 1 minus 2 is negative, so that would be a positive. We put in a 1, 12 times 1 is positive, 1 minus 2 is negative, so that's negative. Plug in a 3, 12 times 3 is positive, 3 minus 2 is positive, so that section is positive. So this tells us we are concave up where? Negative infinity to 0, union 2 to infinity. We're concave down in between those, so 0 to 2. Now I want a graph. Can I get ordered pairs for my inflection points? If x is 0, if you plug a 0 into the original, you get out 0. x is 2, if you plug a 2 in the original, negative 16. Right. Inflection points I like to mark with an X. I'm going to count by maybe 4s. To negative 16 is another inflection point. We just put an X. We only had one minimum at 3, negative 27. Maximums and minimums are points. We're just going to put a dot there. Okay, so I've plotted the only points that I know until I get to this first X, my graph is concave up. So it's curving upward. We also know that we are increasing until I get to this point. No, sorry, decreasing. We're decreasing from the infinity. So I'm curved upward and decreasing. Okay. So like this. At this point, between 0 and 2, my graph is I put this point at the wrong spot, didn't I? Wasn't my x3? You guys are just going to let me go with it? We are curving downward between 0 and 2. We're still decreasing until I get to that point. So your inflection point's very slight change here. After this one, from 2 on, we're curving upward again. After I get to this point, my graph switches to increasing, still curved upward. So it's something along those lines. Any questions there? I think I'm going to stop here. Tomorrow we're just going to practice more of this. So we've learned everything. Tomorrow we're just going to practice more of the graphing piece. I do want to do one quick activity. If you guys will get out your Chromebooks and look at Google Classroom. Posted this handout that had matching graphs with their derivatives. So 1 through 6, these are the original functions. A through F is the derivative. I want you guys to take a couple minutes and see if you can match them. You can do it on your back of your notes or something. Just put 1 through 6. See if you can figure out which derivative will go with each. And you guys can talk to each other if you need to, but I just want you to take a couple minutes to try to figure that out. Based off what we know with maximums. So if you're looking at it, the first one, this graph starts out increasing. Then it's decreasing until a little before 3, and then it's increasing again after that. That means the derivative should be positive, then negative between like 1 1/2 and 2 3/4, and then positive after that. So which one went positive, negative, positive? E. It was positive, negative in between, and positive. So number 1 is E. Number 2. My graph was increasing until I get to 0, decreasing afterwards. So the derivative is positive until you hit 0, negative after 0. So that one is A. Positive and then negative. Okay, number 3. This one is decreasing until you hit 0, increasing after that. So it's negative and then positive. So that would be F. Okay, number 4. This one is decreasing. It has a little hiccup in it, but it's still decreasing until you get to almost 2, and then increasing after that. So we are negative until we get to about 1.75, and then positive after that. That's D. You know, it's got this extra little hoop in it, but it doesn't matter. It's negative that whole time. Alright, this one. Decreasing until you hit negative 1.5, then increasing into positive 1.5, then decreasing. So we should be negative, positive, negative. So that one is C. Remember, this is the graph of sine. And what have we said the derivative of sine is? Cosine. Isn't that a cosine graph? Alright, this one is decreasing the entire time, so its derivative is always negative. So that would be D. Okay. We'll try another one of these maybe tomorrow, looking at some graphs some more. So, the handout I gave you is your homework. You guys listening? The front side, all you are doing is finding your concavity there. So basically do your second derivative, find where it's 0, and then tell me the concave up and concave down. The back two, I want you to try to graph this. Okay, so like the last example we did. We're going to practice more of that tomorrow. But I just want to see, these are both polynomials, so they shouldn't be too ugly.